So we have two goals in this lesson. The first is to explore a little bit how the trig ratios are related when we look at complementary angles. Remember, complementary angles are angles that add to 90 degrees. The second part is there are several angles that we use over and over again, and so it's really helpful to have a way to remember them. And so we're going to look at a special pattern will help us remember the trig ratios for certain angles. So I would like you to copy this triangle. This is triangle ABC. It's a right triangle. And the two acute angles are at vertices A and B. And we're gonna give the measures for those angles. Is the measure of angle A is alpha, the measure of angle B is beta. And so the first question is, if I add alpha plus beta, what should I get? The second question is, how can I show this ratio of side BC, this leg, to the hypotenuse AB in two different ways? So if you will copy that and then pause the video while you answer those questions, and then we'll continue in a moment. All right, so we're back, and the fact that the alpha and beta are the two acute angles of a right triangle, we know the sum is a right triangle, or any triangle, is 180. So if I use up 90 here, that means these have to add to, the two acute angles have to add to 90 degrees. So alpha plus beta equals 90. The second question is, how can I show the ratio of BC in two different ways? Well, one way is if I'm looking at relative to angle A, right? So if I said the sine of, you could either say A or you could say alpha. I'm going to use alpha. So the sine of alpha is going to be BC, opposite, right, over hypotenuse. So remember, the sine is the ratio opposite over hypotenuse. So sine of alpha is the opposite over hypotenuse. That is BC over AB. The other way to do it is to use the other angle. And so if I'm looking at angle B, which is measures beta, and I look at the adjacent side, which is side BC, and the hypotenuse, that's going to be the cosine ratio. So cosine, remember, is adjacent over hypotenuse. Now, I don't expect you to have those memorized yet, so of course you can look at your notes. So if I say cosine of beta, that's going to be equal to BC over AB also. So what can we say about the sine of alpha and the sine of beta? I said that again. What can we say about the sine of alpha and the cosine of beta? Well, they're the same measurement. So the sine of alpha is going to be equal to the cosine of beta, and vice versa, right? We could do it the other way too. We could say sine of beta equals cosine of alpha. So all that's saying is, this is the way we're writing it, but what's it saying is that if two angles are complementary, they add to 90 degrees, that the sine of one angle is going to be equal to the cosine of the other angle. So I'd like you to make a note of that relationship in your notebook. If two angles, angle A and angle B, are complementary, then the sine of angle A equals the cosine of angle B, and the cosine of angle A equals the sine of angle B for complementary angles. So here are two problems that we can solve using that relationship. So the first one says the sine of theta is equal to the cosine of 25 degrees. What do we know that can help us find theta? See if you can think about this. Pause the video, write this down, and see if you can figure out what theta is. All right. Hopefully you were thinking along these lines. So these two angles, because the sine is equal to the cosine of theta and 25, we can conclude that theta plus 25 has to equal 90. They have to be complementary, because when they're complementary, then their sine of one is equal to the cosine of the other. And so then we can just use simple algebra. So remember, theta is like it's a letter. It's not our letter, right? It's not a U.S. English letter. It's a Greek letter, but we use it just the same. So this is the equivalent of saying x plus 25 is 90. So we're going to subtract 25 from both sides. And 90 minus 20, that's 70, and minus 5, that means theta is going to be 65 degrees. And we've solved that. So similarly, you should be able to solve the problem below it. So the sine of 80 is equal to the cosine of theta. So pause the video and see if you can solve that, and I will show you the answer in just a minute. All right, so we're back, and again, because the sine of one angle is equal to the cosine of the other, we know that they are complementary angles. So 80 plus theta has to be equal to 90. So we know theta is 10. All right, so here are two additional problems. They're slightly a little more complicated, but not much. Pause the video and see if you can figure out what angle theta is equal to. All right, we're back. All right, so the first one we have is the sine of theta is the cosine of theta plus 10. So our reasoning is that because the sine of one angle, and remember, this is one angle, theta plus 10 is just another angle, right? So, whatever it is, it's 10 more than what theta is. But the fact that the sine of one is the cosine of the other means that they are complementary. So theta plus 10 has to equal 90. And remember, this is just like the variable x, and only we're using the Greek variable theta. So we have 2 thetas plus 10 equals 90. And so I'm running out of room, so I'm going to go up here. So 2 theta is going to be 90 minus 10, which is 80. And what number can I double and get 80? Well, theta has to be 40. So we know one angle is 40 degrees. The other angle is 40 plus 10. It'll be 50 degrees. And so that is the solution. And for our other situation, we have the sine of theta minus 45, whatever that angle is cosine of theta. So we know theta minus 45 plus theta is going to be 90. So 2 theta minus 45 is 90. So I'm going to add 45 to both sides. So 2 theta is 135. And so I'm going to take half of that to find out what theta is. Half of 100, well, that's 50. Half of 30 is 15. Half of 5 is 2.5. So that means theta is 67.5. And of course, so this would be 67.5 for this angle at the cosine of theta. And then we have the other angle is going to be 67.5 subtract 45. And so we would have 5, 2, and 2. So it'd be 22.5 for the other angle. So this brings up the question, for what angle measure must the sine and cosine have the same value? So pause the video and think about this for a minute. See if you can think of what angle has the same sine and the same cosine value. All right, and back. Hopefully you paused it and you thought a little bit about it. Well, we could set up an equation if we're not sure. So the sine of this angle has to be equal to the cosine of that angle. And that tells you that that these angles, which is the same angle, it's an angle that's complementary to itself. So theta plus theta has to equal 90 degrees. And we can solve this. 2 theta is 90. Half of that would be 45. So it turns out for a 45 degree angle that the sine and the cosine are both the same. And that's going to be important because we're going to look at a special triangle that is a 45 and a 45 degree right triangle. And of course, that means that this triangle is isosceles. So for isosceles right triangles, both the sine and the cosine of the acute angles are the same. All right, so we're going to look at a kind of a fancy picture here, and we're going to be referring back to these ratios of the sine, opposite over hypotenuse, cosine, adjacent over hypotenuse. You can see here that I drew a red triangle inside the arc of a circle, and you can see one vertex of the acute angle is on the origin of the origin of the graph, and the other vertices, one is on the circumference of the circle, and the other one is on the x-axis here. And the idea is this: we want to see that what's going to happen. I want you to picture this point B moving along the arc of this circle, and as it moves, it's going to change the shape of that triangle. And I've got two pictures here because we're going to look at one. The first one we're going to look at is as point B moves to the left. What happens? How does the sine and cosine change? The other picture we're going to look at as B moves to the right. So we'll just ignore the second one for right now. And we want to think about what's happening to the sine and cosine of that triangle. The reason we put we drew it inside a circle is for this reason, because the hypotenuse is always going to be the radius of this circle as this point moves on that circle. So the hypotenuse is never going to change value. It's always going to be the same. But what's going to happen with the A and the B as we move, for example, if I look at, let's pick this point right here, and I'm going to draw another right triangle. So I'm going to draw this. And so what happened is I moved point B from this original position to this new position on the circle. When I did that, the hypotenuse, you got to use your imagination now because Mr. Benson's drawing with his finger, but this hypotenuse is a nice straight radius of the circle, just like this one. All right, and so what's happened to the hypotenuse is it's exactly the same. So if we just think about the sine, the hypotenuse of the original triangle and the hypotenuse of the new triangle, it's the same number on the bottom. But if we're thinking of the opposite side, so here's angle theta right down here. Angle theta was smaller and now it got bigger, right? So in the green triangle, the angle theta is larger than it was originally. But what happened here to the opposite side? Well, you can see this length, this vertical length A, has now increased in size. And so the sine the numerator has increased, but the denominator stayed the same. So the conclusion we can make about the how the sine is going to change is the following. The sine of theta is getting larger or bigger, right? Because what's changing is the opposite side is getting larger. The hypotenuse, because it's the radius of the circle, doesn't change at all. All right, now let's think about what's happening with the cosine of theta. So when I look at the cosine of theta, the cosine is going to be the adjacent side. So here's theta. The adjacent side is here, and then over the hypotenuse. So cosine is adjacent over hypotenuse. And so, again, the hypotenuse is not going to change. But the adjacent side, you can see that as this point B moved, did the adjacent side get larger or smaller? And it looks like it got smaller. And so the cosine of theta is getting smaller. So sine got bigger, cosine got smaller. All right, now I want you to even imagine something even weirder. So what happens when this point gets all the way to the y-axis? Well, you can see that we no longer have a triangle because both the hypotenuse and the vertical distance are exactly the same. So the hypotenuse is equal to the opposite side, even though there's really not an opposite side, but you got to kind of imagine. So we had this length right here. It's getting bigger and bigger. When you get to this angle right here, the angle theta is getting bigger. Now angle theta is a 90-degree angle, and the length of the hypotenuse is exactly the same length as the opposite side. So this opposite side and the hypotenuse are the same length. That means the sine of that angle, which happens to be 90 degrees, So the sine of 90 degrees is going to be equal to the fraction where the numerator is the same as the denominator. It's going to be equal to 1. So that's one big idea. The other big idea is to look at the cosine. So what happens when we look at the cosine of 90 degrees? Well, let's think. So we can see, we said the cosine was getting smaller because this horizontal length was decreasing. And when you get to be a 90-degree angle, there is no horizontal length at all. It's 0. The hypotenuse, or that length to the edge of the circle, the radius, is still the same, but the adjacent side is now 0. And so we can see that the cosine of 90 degrees is 0. Right? So that is the first time that we've talked about sine and cosine ratios for angles that were not acute angles. So we now know what the sine and cosine is for a 90-degree angle. All right. Let's look at the other situation. So what happens if I move point B in the other direction? So what if I move it this way? So let's think about if I put it right here. What's happening to the sine and the cosine? So which got bigger and which got smaller? So I can see that this hypotenuse again stays the same, but I can see that as B moves down the arc of the circle here, that this vertical height is decreasing. So the opposite side to theta, the opposite side, instead of being nice and big like it originally was, it's much smaller. And so the sine is decreasing. So the sine is getting smaller. Sine of theta gets smaller. And comparatively, the cosine, which is using this horizontal length, you can see that originally it was this long, and now in the green triangle it is much longer. So the cosine is getting larger. Right? And we're going to imagine again what happens when this green point actually reaches the x-axis. Well, first of all, let's talk about the angle. As this moves down, the angle is getting smaller and smaller. And at the point where it actually reaches the x-axis, we don't have any angle left. It's 0. The hypotenuse length, C, is now right on the x-axis, so the triangle has an angle of 0. It's not a triangle, but the angle has a measure of 0. And at that point, we can see that both the adjacent side and the hypotenuse are equal to each other, and so we know the cosine of a 0-degree angle is equal to 1. And the sine of a 0-degree angle, well, there is no vertical height left. So this vertical height, which was A, and it got smaller, now it's right has a length 0, and so the sine of an angle of 0 is also equal to 0. So those are the two big ideas, that the sine of 90 degrees is 1, the cosine of 90 degrees is 0, the cosine of 0 degrees is 1, and the sine of 0 degrees is 0. So take a minute and copy this table into your notebook. I'm going to talk while you copy a little bit. So the idea behind this is that we are going to use the trigonometry of certain angles over and over again. And those angles are 0, 30, 45, 60, and 90. They just come up a lot. And so eventually you're going to memorize these values just like you do in your multiplication facts. You'll probably do that in Algebra 2. And so for us, though, what we're going to do is we're just going to be able to use a cool pattern to fill in this table. All right, if you're not done making your table by this point, just pause the video and finish. And then we're going to fill in the table. So here's how this cool pattern goes. This is the pattern of sine for these angles. And the pattern of sine goes like this: square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Real easy to memorize. And then, of course, we can simplify this. So the pattern is, we're gonna write it like this to help us memorize it. But square root of 0 is 0, and 0 over 2 is just 0. So sine of 0 is 0. Square root of 1 is 1, so this is a half. So this will be a half. And square root of 2 over 2, well, I can't simplify that, so that's square root of 2 over 2. Square root of 3 over 2, can't simplify that. Square root of 4 over 2, well, square root of 4 is 2. 2 divided by 2, that's 1. And remember, the sine of, if two angles are complements, right, and these are complements, right, if we look at the pattern here, we have 0 and 90, that's complementary, 30 and 60, and 45 is its own complement. So if we use that pattern to fill it in, I know that the sine of 0 is the same as the cosine of 90, so this would be 0. And the sine of 30 is the same as the cosine of 60, so this would be a half. Of course, the 45 is its own complement, so it's got the same sine and cosine. And then square root of 3 over 2 and 1. So if you look at this, you can see that sine moves this way, cosine goes exactly the opposite, right? So we have 0, half, square root of 2 over 2, square root of 3 over 2, and 1. It's this pattern. And the cosine goes in the opposite direction, 0, 1 half, square root of 2 over 2, square root of 3 over 2, and 1. It goes in the opposite direction. So copy this triangle in your notebook, and we're going to use our knowledge of the trigonometry ratios for a 30-degree acute angle to find the lengths A and B in this triangle. And so we know the hypotenuse. So the sine is going to be the opposite over hypotenuse, so that should allow us to find length A. The cosine is going to be B over hypotenuse, the adjacent side, so that should allow us to find B. So if we look at our table, we should be able to look up our sine and our cosine. So the sine of angle 30 degrees and the cosine of angle 30 degrees. And the sine is 1 half. The cosine is the square root of 3 over 2. Now, you remember, this is just a number. It's an irrational number, so we write it like this if we don't want to estimate it. If you estimate it, you would have to round it. And so we're just going to leave it in this format, which is common. So the sine, we have to remember, means opposite over hypotenuse. The cosine is the adjacent over hypotenuse. So that's going to help us set up our ratios. So we have 1 half, which is the sine, and that's going to be equal to the opposite side, which is A over 3. And so then we cross multiply. We have 1 times 3 is 3, is 2A, and A is going to be equal to 3 divided by 2, which is, you can either write it as the improper fraction 3 halves, or you could write it as 1.5. I'm going to leave it as 3 halves. So this is 3 halves. The cosine is the square root of 3 over 2. And remember, the cosine is the adjacent side, which is B over the hypotenuse, so this is going to be equal to B over 3. And so I have cross multiply, I have 2B equals 3 square root of 3, and then I'm going to divide by 2, so B equals 3 halves times the square root of 3. Or you could write it as 3 square root of 3 over 2 probably. So this would be 3 square root of 3 over 2. So those are the exact answers, right? So this is not a problem. We could write it as a decimal 1.5. This is the exact length for side B. If I wanted to write it as a decimal, I would have to do 3 times the square root of 3 divided by 2, and then decide how accurate I need it to be to round it. So the next problem is a little different because in this case, I do not know the hypotenuse. And when you don't know the hypotenuse, depending on which of the side, whether I know the opposite or the adjacent side, I'm going to have to be choosy, or else I could use the tangent, and that would work. But when you don't know the hypotenuse, and we're not using tangent right now, we have to be choosy. So if I tried to find the sine, for example, that's A over C. Well, that's two things I don't know. So we're going to start by using the cosine. And then once we have the cosine of 30 degrees, that's going to be equal to what? The cosine of 30 degrees is the adjacent side over the hypotenuse, so that's 3 over C. Now I have to know what the cosine of 30 degrees is. course, we know from our table it's the square root of 3 over 2. So this is the square root of 3 over 2. It's equal to 3 over c. And then we can cross multiply. So I have square root of 3 times c equals 6. And then I'm going to divide by the square root of 3. And we have c equals 6 divided by the square root of 3. That's a perfectly good mathematical answer, but we don't like radicals in the denominator. So remember, the trick is to multiply by a giant 1, square root of 3 over square root of 3. And that would give us c is going to be equal to 6 square root of 3. The square root of 3 times the square root of 3 is the square root of 9, which is 3. And now I can see that, well, 6 divides by 3. So the final answer is going to be 2 square root of 3. So side C, the hypotenuse, is going to be 2 times the square root of 3. And that's the way we would like it written. So if you wrote it as 6 divided by the square root of 3, we would not be that excited about that answer. So now if I want to find the cosine, or the sine rather, of 30 degrees and solve the opposite side, it's going to be okay to do. Notice, you could also use the Pythagorean theorem, right? Now I know two sides of my triangle. So once that happens, I could even use the Pythagorean theorem. So let's go ahead and use sine to find the other side. So I have the sine of 30 degrees is going to be opposite, which is a, over the hypotenuse, which I now know is 2 square root of 3. The sine of 30 degrees we know is a 1/2 equals a over 2 square root of 3. And now I cross multiply. So I have 2 square root of 3 times 1. And then that's equal to 2a. Then I divide by 2. And a is going to be equal to the square root of 3. So this is the square root of 3 for a. And that's it for your notes for today. Thank you.